Convolutional neural network architectures have previously shown to have unprecedented performance in image recognition. Each convolutional layer detects features in the images, which can be used to help classify the image. The use of pooling helps to reduce the number of parameters in the network. However, this results in some information loss, which can be detrimental, for example, in the classification of radio galaxies, especially with the galaxies that have many components to them. For example, if we took the top right part of this FR2 image and rotated it and put it back, we could probably fool the convolutional network into thinking the image is still an FR2. Capsule networks have been invented to address these shortcomings. A capsule is made up of a group of neurons that attempt to extract all the different kinds of transformations you can make to an image. For example, skewing, blurring, changing the thickness, such that the label still stays the same. We used radio galaxy images from the LOFAR telescope, which included the original images, as well as images where noise and unassociated emission had been removed. We compared two convolutional network architectures against that of different capsule network architectures. We found that both our convolutional network architectures outperformed any variation of the capsule networks. As can be seen in this image here of an FR1 that has a bit of unassociated emission to the right, the feature maps of the primary capsule indicate that this unassociated emission is preserved, whereas for the same image in one of the convolutional network architectures, the unassociated emission is removed by the fourth convolutional layer. It seems that the capsule network has not successfully learnt to distinguish signal from noise. As a result, when we look at the reconstructions of the images based on the features that the capsule network has learnt, we see that they are inaccurate, where FR2s are reconstructed as diffuse blobs, unresolved or compact sources are reconstructed as concentrated blobs, and FR1s are somewhere in between. It appears that for the number and the type of images that we had, the convolutional networks perform better than the capsule networks. It's possible that the pooling operation may provide advantages too, such as the removal of unassociated features and noise, as well as provide more degrees of freedom for the variability of the FR1 and FR2 morphologies. Perhaps with the use of more original training images, especially those in the FR1 and FR2 classes, we would see that the capsule networks perform as good as or even better than the convolutional neural networks.